right, we are going to look at a lot of different center type points in triangles. And if you don't pay close attention to what the diagram involves, you might think some of these center points are all the same, and they're not. They're a little bit different, they're made up of different things. In certain triangles, like in an equilateral triangle, a lot of the center points that we're going to be talking about will be the same location. So it's not good to use that as an example. You need to go with like a scalene type of triangle to see the differences between these. And the project that I'm going to talk to you tomorrow about is taking these four centers that we will talk about between today and tomorrow and graphing or constructing them on a triangle. Because three of them have a unique relationship, they form what's called the Euler line. I want you to come up with the Euler line and which points they are. So you'll have to do some constructions for a project, and I'll talk to you tomorrow about that. But the center points are going to be a circumcenter, an incenter, a centroid, and an orthocenter. Those probably some terms you haven't heard before, so some new vocabulary for you. So let's see what those are. Today we'll talk about two of them. The term equidistant is used in a lot of the theorems in this chapter. What's it sound like equidistant probably means? The same distance or equal distances, exactly. Our key to this chapter is equal distances from where. Now from where to where is equal. And sometimes it will be from the center point to the side of the triangle. Maybe it'll be to the vertex of the triangle. Maybe it'll be to the ends of a segment. So that's the type of thing we're going to have to focus on as we try and organize in our brain what this chapter's about. So equidistant just means the equal distances, equal lengths, basically. All right, let's start out with the perpendicular bisector theorem and its converse. We, in our bell ringer, reviewed what a perpendicular bisector is, and it was like a line that cut a segment in half and made a 90-degree angle with it. So this theorem tells us more about perpendicular bisectors. And as you're drawing the hypothesis, think about what you're drawing. You're drawing the hypothesis that's in words over here. If a point is on the perpendicular bisector of a segment, that's what the hypothesis picture is showing. X is a point, kind of made a square point, but X is a point that is on the line that makes a 90-degree angle and cuts that segment in half. So it's on the perpendicular bisector. They've written it kind of in words or in symbols there. You can put it in words, whatever works for you. I think now you probably have an idea if the visual works better for you or if the wording works better for you. And make your notes what works best for you. Okay, hypothesis. A point is on the perpendicular bisector of a segment. Then the conclusion, that point, is equidistant from the endpoints of the segment. So in symbols that would mean x to A and x to B are the same. So if you measure from x to A and you measure from x to B, those will be the very same length. It's equidistant from the ends of that segment. The second one is the converse of that. So notice the wording is backwards from the first one. If a point is equidistant from the endpoints of a segment. So your picture this time probably doesn't even have to have that line in there, but X is the same distance to A and to B. X is equidistant from the ends of a segment. Then it is on the perpendicular bisector. So this that they wrote over here tells you that segment XY is perpendicular, and with the YA and YB being equal, it bisects. It might work if you just put X is on the perpendicular bisector. That might mean more than what the symbols are showing. We did a construction that really supports this or ties into this. And I'll just try and give it up on the board that way. Okay, a perpendicular bisector construction looked like a midpoint. So we've got a segment, From each end, we did the same amount, swung an arc from the left and from the right. And then we connected those 2 points. Split it a little bit. So what we really do when we do that construction is we take this point, which is the same distance from here and here, because we didn't change our compass. We connect that point, which is on the perpendicular bisector, to this point, that again is equidistant. So we're connecting 2 points that are equidistant from the ends. So each of those points is on the perpendicular bisector. So that supports why that's a midpoint, and why it's actually constructing a perpendicular also. So it kind of ties into the converse theorem there. Everybody got notes done? So the locus is a word that I don't use very much, but your book has it here and there. It says the locus is a set of points that satisfies a given condition. So if they were defining perpendicular bisector, you might see in the book that they say it's the locus of points in a plane that are equidistant from the endpoints of the segment. So if I would do all the points that are along here equidistant from each end, like if you picture that construction being done over and over and over with the compass changing just a little bit, that set of points creates the perpendicular bisector. So that's their definition, locus of points. All right, so I showed you how to construct it. We've done that construction before. Let's see if you can apply those theorems and tell if it's the theorem or the converse. Find the measure of Mn. How long is segment Mn? How much? 2.6. Is this the perpendicular bisector theorem or the converse of the perpendicular bisector theorem? Look at the hypothesis. What do we have? Do we have a perpendicular bisector? The markings, yes, indicate it is. So is that the original or the converse? Should be the original one that we were using here. So it said that n was equidistant from each end, so 2.6 was correct. Second example, do we have a perpendicular bisector? I see the perpendicular marking. Does it tell us that it bisects? No, it really doesn't tell us that those are the same. So I don't know if that's just a perpendicular or a perpendicular bisector. So I can't use the original theorem. What's the converse say? If a point is equidistant from the ends of a segment, notice A is equidistant from B and C. Okay. So then it, A, is on the perpendicular bisector of that segment. So that tells me that this is not only perpendicular, but it does bisect. So that converse can support that it bisects. So if this is 12 and this is 12, BC is 24 for the answer. Question? And how about an algebra type? Is there a perpendicular bisector? Okay, yes. And a point that's on it is U. So it's the same distance from U to T as U to V. So how would we set up the problem to solve it? Those equal each other, correct. And then in the end, we're not going to stop once we found X. We're going to have to substitute in to find TU. So substitute in 3 times 6.5 plus 9, 28.5. If you want to check to make sure you did the problem right, substitute it into UV and make sure that you get the same value for that. All right, now we're going to try and see if your minds remember how we wrote the equation of a perpendicular bisector. How did we do that in chapter 3? Writing the equation of the line that is the perpendicular bisector. You might want to find a place on your notes so that you can have another sample. Okay, what are some things going on in your mind? What's the opposite? Okay, what's the opposite reciprocal have to deal with? Okay, so if we find the slope of that segment, we don't want to use the same thing to write the equation of the perpendicular bisector. We want to change it. Okay. Find the slope of that one, and then we're going to change it for our equation. What's the slope of segment AB? Which formula is the slope up here? Middle one. The third one down is the slope. That's what you're doing right now, right? And you get, what, 4 over 6? Reduces to be 2/3? So when we write the equation of the perpendicular bisector, what slope should we use? -3/2. What point do we want the perpendicular bisector to go through? The midpoint. So now we need to find the midpoint of those. So what's the midpoint? The second one down, correct. What's the midpoint end up being? Add together and divide by 2. 1, 4. How did we write the equation of the line from that? What form did we use? Probably point slope. We got y minus 4 equals 3/2. Parentheses x minus 1. Didn't really say what form to leave it in. So that's the point slope form, and if you converted it, y equals -3/2 x plus 5 1/2. So perpendicular bisector, I think there's another equation or two on the assignment. We did that earlier, so hopefully that's a review. All right, now let's try and put all the perpendicular bisectors in one triangle. Okay, it says since a triangle has 3 sides, it has 3 perpendicular bisectors. When you draw or construct the perpendicular bisectors, you find they have an interesting property. So rather than exactly what it says there, on your notes, there are some triangles drawn there, kind of small ones. I want you to do the best you can to draw the perpendicular bisector in each triangle and of every side. So let's kind of maybe go bottom side to start with. So you've got one triangle here. Okay. So draw its perpendicular bisector. So as best you can, estimate where the middle is. We want that to be the midpoint. Draw your perpendicular bisector. Try and make it at a 90-degree angle. Do that on the next one. And the last one. Notice these are different kinds of triangles. The last one's supposed to be a right triangle. Okay, now turn your paper and do that from every side. So turn it and see if you can do the perpendicular bisector from the left-hand side. Why turn your paper? I think you're probably better at estimating when you're looking at horizontal and vertical. do a perpendicular bisector on every side. Are you finding something interesting about them? They should all three cross somewhere. Something kind of like that is what you're thinking of. The perpendicular bisector you're drawing does not always, and more often than not, it does not go through a corner of the triangle. So if you're trying to keep it going through a corner of the triangle, no, that's not drawing a perpendicular bisector. Okay, where they should end up, go to this one. Your first triangle, all the perpendicular bisectors should meet inside the triangle. Now your second one, they actually end up outside the triangle. So if you don't have yours connecting, you might tip them a little bit more. You probably aren't getting your right angle very good. That one is outside the triangle. And on the right triangle, it ends up being right on the hypotenuse. Now the point that you're creating, or here's some terminology, I guess. Let me back up. If those three lines, if two or more lines, actually three or more lines, meet at one point, we call them concurrent. Meaning all three or more lines meet at one point. They're concurrent. Where they meet is called a point of concurrency, and it has a certain name. These that we just created are called a circumcenter. Okay, so the circumcenter is where the three perpendicular bisectors come together. That's their point of concurrency. It's called a circumcenter. So I'm going to write up here circumcenter. What's it made up of? The three what? Three perpendicular bisectors. It's where they meet. Sometimes it's in the triangle, sometimes it's outside the triangle, sometimes it's right on the triangle. Depends what kind of triangle you have. Okay, now to tie into the theorem that's coming up, if you look at each perpendicular bisector separately, okay, this is a point that was on this first perpendicular bisector I drew. So that theorem we had just a little bit ago said that point is equidistant from the ends of the segment. So that point is the same distance to that corner and to that corner. Those are the ends of my first segment that I bisected. Then when I went over here, this point is equidistant to that end and this end. And notice that on this one, equidistant those ways. The three purple segments I drew will have the same length. Same happens here. Even though it's outside, it's the same distance to this corner and this corner, the ends of that segment. Same distance from the ends of this segment. That doesn't look real good, but. And then same distance from the ends of that segment. So again, the three purple segments would be the same length. Here also the same. We'll do this with a compass eventually. Those three segments, the purple segments in each one are congruent. Now if you're good at drawing circles, we can draw a circle because a circumcenter is the center of a circumscribed circle. It's the circle that goes around, touching all vertices of the triangle in this case. So can you draw a fairly good circle around? Not too bad, I don't know, maybe it's worse than I thought. This one looks kind of weird because it is a big round part over here. The triangle is in just a smaller portion of it. That triangle gets, or circle gets really big. So this would be like a semicircle, and then the rest of it. For your notes, it might be easiest to, down by that definition, draw a circle and then put the triangle in there correctly. So the circle goes around the shape. That's what the term circumscribed means, going around. And it specifically touches all vertices. Now if you visualize that circle, that might help you get the equidistant idea, because those are the radii of the circle. Bad circle. All right, so circumcenter goes with a circumscribed circle, which is made out of the 3 perpendicular bisectors, and that circumcenter is equidistant from the vertices of the triangle. That equidistant idea is, if you turn your page maybe, circumcenter theorem. The circumcenter of a triangle is equidistant from the vertices of the triangle. All those lengths are the same. Remember, it was 1 perpendicular bisector at a time. Equidistant from the circumcenter to each vertice. So when I look at a lot of the pictures in this chapter, what I have to do is focus on, okay, this point of concurrency, point P, and then look, okay, this red thing is a perpendicular bisector. And this one's a perpendicular bisector. So if I think back to separately perpendicular bisectors, it helps me remember the equidistant idea that's going on. As we do more and more pictures that look about the same, maybe that will help, and focus on that center point. All right, let's take a look at, here's a type of problem. Segment DG, EG, and FG are the perpendicular bisectors of equilateral triangle ABC. Doesn't look very equilateral. I probably stretched it one way. So those are perpendicular bisectors, although they don't have every tick mark on the picture. Find GC. What did the theorem just say? Perpendicular bisectors come together to make a circumcenter. Okay. Circumcenter, that theorem says, is equidistant from the vertices of the triangle. So G is the same distance to A, to B, and to C. Did they give us any of those lengths? Yeah, GB is 13.4. So how long is GC? 13.4. How long is GA? 13.4. So it's the same distance to every vertex, all the vertices. About this one. Find GM Point Z is the circumcenter of the triangle. 14.5? Why? Okay, right. If this is a circumcenter, then the things that came together were perpendicular bisectors. So if this is a perpendicular bisector, that supports this one being 14.5. Question? What else could we find in this picture? Do we know ZJ's length? Okay, 19.9. We also know ZH, 19.9. How about KG? Be careful. Yeah, it's the same as 18.6. How about LJ? I don't see that one right off. How about LH? Don't see that right off, but isn't this a perpendicular? We know this side. We know this side. How can we find the missing side of a right triangle? Pythagorean theorem we could do to find that. So we can use some things that we've studied previously to help us out. They didn't need us to find all that stuff, but good thoughts. And had we found JZ, yeah, we did that just a little bit ago, 19.9. So we got that one done. All right, let's switch our focus to angle bisectors instead of perpendicular bisectors. Okay, visit with your partner, first and second row, third and fourth row, and then we'll kind of clear up in the back there. If somebody's gone, find a partner around to talk to. Just discuss what an angle bisector is.
A ray that cuts an angle directly into congruent angles.
And draw one accurately on your paper. Draw one as accurate as you can on your paper. Mark it appropriately. See if your partner is doing the same kind of marking. Something like that? I know you didn't grab a protractor, so you just got it estimated by visually looking. Let's take a point that is on the angle bisector and see if what it says up there is true. What the theorem is saying is if you have a point on your angle bisector, then it is equidistant from the sides of the angle. When you measure from that point to the side, remember we talked about you have to go the shortest perpendicular distance? So from that point, go perpendicular to the side, and go perpendicular to the side here. Those two lengths will be the same if that really was an angle bisector. Did you estimate well? So your angle bisector theorem, if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. That picture up there is what I did on the board. Probably similar to what you did. Notice it's perpendicular with the side. The perpendicular isn't at the angle bisector, it's at the side. We could prove that really easy. I didn't talk about proving on that last one. We could prove AC and BC are congruent or equal. Triangles, got those angles congruent, got the right angles congruent. Segment PC, congruent to PC reflexive. The two triangles are congruent because of, well, last chapter, why are the triangles congruent? Oh, some t-shirts?
Yeah.
Am I supposed to be handing those all out? Okay, thank you. I'll see. Probably have the office aides do that. Okay, so the two triangles are congruent by angle, angle, side. And then these are the same because of CPCTC. So you could do a proof of this theorem fairly easily. I think these are the pie shirts. Anybody order a pie t-shirt? You got a few? Okay, and the converse is if a point is in the interior of the angle, if it's equidistant from the sides, then it's on the angle bisector. So the reverse situation again. So if you want to put C is on the angle bisector. So the equidistant is going to the sides of the angle, not to the vertices this time. Let's try some before we put it into a complete triangle. Done with that? Nope. Okay. The locus of points, they might use that terminology again. Okay, how long is BC? Do we have an angle bisector? Okay, yes. So angle bisector, so 7.2 was correct based on that theorem, not its converse. Do we have an angle bisector? Okay, not labeled, so what's the converse say? Okay, so if a point is equal distance from each side, which it is, and they mark that we're measuring it perpendicular, then what's the conclusion? Okay, this is on the angle bisector. So yes, the angle is bisected by that converse. So if EFG was 50 degrees, what is EFH? Which would be what? If this whole angle is 50? 25 and 25. And the angle one here, converse theorem again. So they would be equal because it would bisect. So I think you know how to set those equal and solve. All right, let's try putting them all in one triangle and then find what's called the incenter. I think you'll find those same triangles if you turn your page in your notes. Okay, now this time when you draw, you're going to be doing angle bisectors, not perpendicular bisectors. So we're going to create what is called the incenter. So on your triangle, try to cut the angle in half. So visually, cut each one in half. So where those meet will create what's called the incenter, which is different from the circumcenter. Do that on all three. getting any of them to be outside the triangle? No. Yeah, not possible to happen. Right. So an in-center always stays inside the triangle. Now, each of those I created are angle bisectors. My markings. Right, a point that's on the angle bisector is equidistant from where? What's the theorem? The sides of the angle, right. So, from this point, if I measure perpendicular to this side and perpendicular to this side, those should be the same length. And if I go perpendicular to this side, that should also be the same length. So perpendicular to every side. Purples are all the same length, or should be all the same length. Notice they are not perpendicular bisectors. They just make a 90-degree angle. So that's how it's different. Now there is a circle that can be involved. The circle does not go on the outside, it actually goes on the inside. So think of these purple segments as radii of a circle. You would have a circle that goes on the inside of each. That's called an inscribed circle, not a circumscribed circle. Making sense? Okay, so you've got the centers. So no matter what kind of a triangle it is, the in-center is always on the inside. Your circle is an inscribed circle, touches all sides. So the inscribed circle is on the inside of the polygon. All right, so what's the theorem say? The theorem tells you about that it's equidistant from the sides. So the incenter of a triangle is equidistant from the sides of the triangle. Incenter is made up of the 3 angular bisectors meet. Same distance to each side. So the pictures are ready. So here's a picture with the angle bisectors in it. I don't know why they choose not to put all 3 of them, but this is what they typically did. Just checking on your notes here. So if you want the 3rd one in there for a look, find the distance from P to MN. So how far is it from P to side MN? It's the same distance, since this is the incenter, it's the same distance to every side. 5 they gave you, correct. So 5 was the distance to that side, it's the distance to the side we want also. How about finding an angle? They want us to find the measure of angle PMN. So this angle is what we're after. This other segment up there. Any thoughts going on? Okay, if that was 20 and I drew that in, 10 degrees, 10 degrees. Are there vertical angles here? No, those really aren't vertical angles. 50, this would be 50, wouldn't it? What's this whole corner? 100. What's this whole corner? 20. So what should this whole corner be? The great big triangle, 120, so that would have to be 60. And this was an angle bisector, 30 degrees, 30 degrees. Get there? So we're using the great big triangle to help us out on that. I don't think you can really get there with the little triangles, especially because there's no vertical angles involved. And let's have you do a couple with your partner. Okay, discuss this one with your paired up partner.
Maybe. Think. It should be the same.
Yeah.
So how far is X from PQ? It should be 19.2. There wasn't a whole lot of calculating involved in that one, just identifying that it's equidistant from every side because of it being an bisector. Where the angle bisectors meet. All right, how about find angle PQX? And with your partner, you can discuss that. What? Let's see, QX and RX are angle bisectors.
Or I mean,
X is
I don't know. I don't think it's
Add that. Okay, so X, Y, so then QX would be 19.2.
right. Okay, what are we doing? We're doing the angle. Wait, so you can just say angle 62, right? And then minus that 180. And then roughly.
52. I don't guess the others.
Right, so it's like 30 degrees.
Not of PQR, but it is an angle bisector.
Or you can take the whole. Okay, wait, 52 plus 24. What's that?
Okay, what's some group answers? 52? Any other groups get 52? You did? What are some other ones? I think 52 ends up being right, not because this is 52, but how did you go through it? This corner is 52, this is 24. Add those up, that is 76. So this whole angle is 104. This was an angle bisector, so 52 degrees, 52 degrees. Make sense? Okay, I think that's my last one. All right, so a summary before we work on some homework. We did perpendicular bisectors. A point that's on a perpendicular bisector is equidistant from to the corner or the ends of the segment, which when you put it in a triangle, that's the vertices of the triangle. Angle bisectors are equidistant from the sides of the angle. When you put it in a triangle, that ends up the sides of the triangle. So in center, 3 angle bisectors meet. Circumcenter, 3 perpendicular bisectors meet. Something dawned on me when I was trying to figure out ways to help you remember. Consonant, consonant, vowel, vowel. That works on tomorrow's also. So it kind of narrows down what things come together. All right, so on the board it's kind of a summary of the theorem and definition ideas. But I need some space to write what your problems are, so I'll have to erase a little bit. Okay, so we have page 305. Yeah, we do have 2 pages because the first one didn't have the triangles, but I didn't pick too many off the first page. 304, 1 through 7, 9, 10, 36, 43, 46. The second page is where they put all 3 in the triangle to make like a circumcenter or an incenter. Again, the assignment kind of jumps, so make sure it's down. One through 6, 9, 10, 12, 15, 18. Okay. Those 2 for your assignment. And you probably can get a good ways on that first page, even in the time with the 6 minutes we have remaining. That first page goes pretty quick.